Welcome everyone to the 5th Developer of the Year Michael Wormit Award. About 5 years ago, on March 14 of 2015, the life of Michael Wormit was cut short. It was and still is a tragic loss for all of us. Michael was a husband, a son, a friend, a great colleague, and a great mentor. He was also a part of QChem developers community. We gather here today to remember Michael and to celebrate his accomplishment and his contributions to our community. His life was short, but he left a mark, and his work will continue to make an impact. And this is something which we should cherish and remember. To commemorate Michael's contribution to QChem community, QChem Board of Directors established an award in his name. On behalf of the Board of Directors, let me introduce Michael Wormit Award. The award has been established in August 2015 to recognize excellence in developing new methods and algorithms in the area of electronic structure and implementing these methods in state-of-the-art computer codes within QChem Open Teamware Community Project. The award is given annually, and it includes a certificate, which I will show you soon, and $500 prize. By this award, Michael is remembered for developing state-of-the-art algorithms and computer code for many-body methods and for his leadership in community building, education, and mentoring of junior team members and infrastructure development. Any member of the QChem developers community is eligible for this award, and the selection criteria are scientific innovation, excellence in code development, contributions to infrastructure and developers community. The first award was given in San Diego in 2016 to Evgeny Epifanovsky, and in 2017 to Andrew Gilbert, 2018 Alec White, and to Yonho Lee in 2019. Today, the 5th Michael Wormit Developer of the Year Award will be presented. We have received several outstanding nominations. The board appointed an international selection committee. The committee has chosen 2 winners, as this year is an exceptional year. And the winner of the 2020 Developer of the Year Wormit Awards are Dr. Yuezhi Mao and Dr. Pavel Pochilo. I will introduce them separately, but please join me virtually in thanking Yuezhi and Pavel for their contribution to the company and to the community, and congratulate them on being selected as the recipient of the 2020 Developers of the Year Michael Wormit Award. The second speaker and the awardee is Dr. Yuezhi Mao, and I'm going to briefly introduce him. Yuezhi Mao received his Bachelor of Science degree in Material Chemistry from Peking University in China in 2012. Then he joined UC Berkeley, working with Martin Gordon, and he received his PhD in 2017 in December. The nomination of Yuezhi was mainly based on his PhD at UC Berkeley. His work includes development of crucial infrastructure for QChem, namely fragment methods and Gen-SCF-MAN. The selection committee specifically cited his infrastructure as a significant step toward implementation of new advanced features in QChem, such as second generation of energy decomposition analysis based on absolutely localized molecular orbitals, which he is going to briefly maybe talk today about that, the adiabatic EDA, improvement of constrained DFT, and many, many more. More importantly, Yuezhi has supported other developers generously with advice as well as personal time and effort. A short quote from the nomination letter by John Herbert Yuezhi is by a wide margin the most active developer who is not a QChem employee. So thank you very much. Yuezhi is now a postdoctoral in Professor Tom Markland's group at Stanford, and his current research focuses on the study of non-adiabatic processes in the gas and condensed phase using electronic states obtained from ab initio calculations. Today, Yuezhi will talk about electronic structure method based on absolutely localized molecular orbitals from non-covalent interaction to electron transfer. Yuezhi, the floor is yours.
It is my great honor to receive the Michael Wormit Award, the Michael Wormit Award this year, and I would like to thank QChem for organizing this virtual symposium, which gives me the chance to share my research. Today, I will focus on my development of electronic structure methods based on ALMOs. I will show how this method can facilitate the study of non-covalent interactions and electron transfer. So the ultimate goal of my research is to unravel chemical mechanisms to facilitate the rational design of new catalysts and functional materials or molecules. And in particular, I'm interested in two research topics. One is non-covalent interactions, because they offer new routes to enhance chemical reactivity by modifying the non-covalent interactions in the system. One can modulate the energy profile of chemical reactions. And the second is electron and hole transfer. They form the fundamental steps in many chemical processes, such as photoredox catalysis shown here. And my method development will aim to address the challenge to unravel the mechanisms behind these phenomena or processes and to harness them in chemical applications. And before we dig into the first topic, I would like to give an overview of the technique the core technique for all this method development, which is absolutely localized molecular orbitals. So ALMOs are molecular orbitals assigned to fragments and expanded in the basis functions on the assigned fragment only. So they are quite different from the case of a standard SCF calculation. So in a standard SCF calculation, there is no partition in the system. So the molecular orbitals are expanded in the basis function of functions of the full system. And in the SCF procedure, the global occupied virtual partition is variationally optimized. And also, if the system is charged, then the charge will be delocalized in the full system because there is no mechanism to enforce charge locality here. While in the ALMO setup, we will introduce the concept of molecular fragments, and then the molecular orbitals are expanded in the basis functions on the assigned fragments only. And in the SCF procedure, the occupied virtual partition is optimized on each fragment rather than being optimized globally. And also, you can prove that in an ALMO calculation, the molecular population of each fragment will be conserved, so charge locality can be enforced. And using ALMOs, I have developed a family of methods which can be used to study non-covalent interactions. They can not only decompose intermolecular interactions in closed shell and open shell systems, but also the decomposing changes in molecular properties, such as vibrational frequency shifts induced by non-covalent binding. In addition, in collaboration with Professor Yihan Shao, I have developed ALMO-based analysis for unraveling substituent effects on conjugated systems on the frontier orbitals of these conjugated systems. And today I will focus on the second generation ALMO-EDA and its recent extension to a solvation environment. So energy decomposition analysis is a family of methods which separate a total interaction energy into physically intuitive, meaningful terms. And these methods are particularly good at interpreting phenomena related to non-covalent interactions. And so the ALMO-EDA method essentially provides a physically intuitive path connecting the isolated fragments and the fully relaxed intermolecular complex. So we start from the isolated fragments whose orbitals are optimized separately with fragment SCF, and then we bring them together into the complex geometry without relaxing their orbitals. The energy change of this step will define as a frozen interaction. Then we allow the orbitals to relax on each fragment, and this energy lowering will be the polarization term. And finally, we remove all the constraints and allow the charge to flow between fragments, and the final energy lowering is defined as the charge transfer term. And more recently, we introduced the second generation of ALMO-EDA for DFT calculations. And in this method, we enabled the further decomposition of the frozen term into physically more intuitive electrostatics, Hall repulsion, and dispersion contributions. We also introduced a more robust scheme to separate polarization and charge transfer. So with the second generation ALMO-EDA, we are able to identify the fingerprints of many different types of non-covalent interactions. Here is an example of the adenine-thymine complex, and for the hydrogen bonded and the pi stacked configurations, you can find the dominating interaction component are quite different. And with the ALMO-EDA established in the gas phase, it's highly desirable to extend to enable its use in the solvation environment. This is because there are so many interesting chemical processes occurring in the condensed phase rather than in the gas phase. So we recently developed a method called ALMO-EDA solve to consistently include the solvation environment in an ALMO-EDA calculation. And so the goal is to decompose the interaction energy in the solvation environment, which is the energy difference between the fully solvated complex and the sum of the solvated fragment energies. And as in the gas phase EDA, it can be decomposed into frozen, polarization, and charge transfer components. And for the frozen frozen term, by playing a small math trick here, we can further decompose that into a new term, which is called delta E sol, which describes the change in a solute-solvent interaction energy upon the formation of the complex, as well as the decomposition of the frozen interaction energy as evaluated in the gas phase. And then by separating the electrostatic and the non-electrostatic component of the solute-solvent interaction and combine them into these terms, we are able to achieve a frozen energy decomposition in the solvation environment. And then we perform ALMO and standard SCF calculations in the presence of solvent. So in the calculation of polarization and the charge transfer, the solvation effect will also be taken into account. And first, we would like to validate this method on a simple system, which is a water-sodium complex immersed in different solvents. And here the solvents are modeled by the SMD solvation model, which contains a PCM description for the electrostatic interaction and some non-electrostatic terms. So here, by comparing the results in toluene and water, we found that the electrostatics and polarization are more strongly screened in the more polar solvent, which is intuitively correct. And also we found that the unscreened electrostatics is elect 0. So this dashed line is more attractive in the more polar solvent, and this is because the dipole moment of the water will be larger in the more polar solvent. And if we look into the solute-solvent interaction contribution, we found that and decompose that, we found that in this case it's dominated by the electrostatic interaction, and the non-electrostatic component is of minimal importance in this example. And these all look quite reasonable to us, and we are going to apply this method to study like a complex in CO2 reduction catalysis. And so this iron TPP and its derivatives are a prominent family of catalysts for CO2 reduction to carbon monoxide. And once FeTPP is doubly reduced, it can activate CO2 by donating an electron and form an adduct like this. And in previous experimental studies, it was found that by introducing different substituent groups to also or para position of these methyl-phenol groups, one can significantly modulate the catalytic performance of these catalysts. So for example, by introducing the trimethyl amino group, which is a positively charged substituent to the para and also positions, it can achieve higher catalytic activity at low overpotential, which is certainly favorable. And this similarly can be achieved by introducing a hydroxyl group to the also position here. However, by introducing a negatively charged group to the para position, such as this sulfonate group, the catalytic performance will degrade. So it was conjectured that the through space interaction between, for example, these positively charged groups and the CO2, the through space interaction can stabilize this activated CO2, which lead to favorable catalytic performance. And we are using ALMO-EDA solve to further investigate the mechanism for this modulation of catalytic activities. So here are the results of these substituted complexes and relative to the unsubstituted one. So this is a differential EDA results. And the result is quite surprising to us, because what we found is electrostatic interaction between the positively charged TMA groups and the CO2 is actually strongly attenuated in solution. So for these two, they are not significantly favorable at all. And for this para TMA complex, this is even less favorable than the unsubstituted complex, which is quite counterintuitive result. And we found that in fact, the stabilization achieved by these TMA groups through structure mechanism rather than through space, because this is because the TMA groups, it's a very strong electron withdrawing group, so it can reduce electron density near this catalytic center and then reduce the repulsion with negatively charged CO2. And on the other hand, for the also OH complex, if we look at its the fingerprint of this interaction, we will find it's very similar to a typical hydrogen bond, and this is indeed through space hydrogen bonding, which stabilizes the activated CO2. So what can we learn from these results? So we firstly found that introduced positively charged groups to stabilize CO2 minus may not be that effective in solution because of the screening. And on the other hand, if we can effectively squeeze out the solution and get rid of this damping effect, we might still be able to stabilize the CO2 minus. And so based on that, we designed this new complex, which contains this quite bulky and floppy ligand, and it carries a positively charged methyl imidazolium ring. And we found that this new complex is able to enhance the stabilization of CO2 mainly through the electrostatic interaction. So it's substantially favorable here. And our further study shows that this comes from two different sources. One is hydrogen bonding between the amide group and the CO2, and the second is from the positively charged imidazolium ring. And because this second coordination sphere ligands are quite bulky, they can effectively squeeze out the solvent and achieve very large stabilization from electrostatic interaction. And based on the established correlation, this complex can potentially be a very ideal catalyst for CO2 reduction because it achieves the largest stabilization by far. And besides investigating non-covalent interactions, I have also developed methods based on ALMOs to create diabatic states to facilitate the study of electron and hole transfer. And now we are going to enter the second topic. So electron and hole transfer are fundamental steps in many chemical and biochemical processes, such as charge and energy transport in photovoltaic materials. These two processes are essentially the same, but they are called differently simply depending on whether the system is negatively or positively charged. And the charge-localized diabatic states naturally correspond to the initial and the final states of the electron or hole transfer process. For example, for the hole transfer in this ethylene dimer, the two diabatic states will correspond to the charge localized on either of the ethylene molecules. And these chemically intuitive diabatic states form the basis form the basis of widely used rate theories such as famous Mach theory and many quantum dynamics approaches. However, these diabatic states are not naturally produced by electronic structural calculations, and the special treatment are needed, which are the diabatization schemes. And our goal is to develop a DFT-based diabatization approach, which can give variationally optimized diabatic states and get easy access to the associated nuclear forces. And we also hope to evaluate the couplings between the diabatic states accurately and also produce consistent results for asymmetric systems, because this is not satisfied by some of the available methods. And we use ALMOs again to construct these charge-localized diabatic states. So here we consider a hole transfer system as an example. And we can construct these ALMO states from fragment orbitals. For the initial state, we have a positively charged donor and a neutral acceptor. So, and we can perform SCF calculations on each of the fragment separately and then concatenate their orbitals. This is initial guess to the initial state for the electron transfer, hole transfer here. And for the final state, we can do something similar. We just need to switch the population of the two fragments and do the fragment SCF and then concatenate their orbitals. Then we just launch the ALMO SCF calculations, which will give us variationally optimized diabatic states. And now we want to accurately calculate the coupling between ALMO-based diabatic states, and so the coupling between two symmetrically orthogonalized ALMO states can be determined using this equation, and it will require the diagonal and off-diagonal elements of the Hamiltonian matrix in the non-orthogonal ALMO state basis. So we can use a multi-state DFT approach to calculate these matrix elements. So for the diagonal elements, it's quite intuitive to use the Cohen-Sham energies associated with each of these diabats. And for the off-diagonal elements, the original MS-DFT method first calculates the coupling between two Cohen-Sham determinants using Hartree-Fock Hamiltonian, and then apply a correction for the exchange correlation contribution, which is estimated as the average of the energy difference between Cohen-Sham and Hartree-Fock for each determinant. However, we found that this method systematically overestimates the diabatic couplings in most of the hole and electron transfer cases. And we proposed a modified approach, which is named as ALMO-MS-DFT2. And in this method, we use the exchange correlation functional of the symmetrized transition density between each of these diabats to calculate this off-diagonal element. And this method is internally more consistent because in the limit A equals B, you will recover the Cohen-Sham energy of each of the diabat from here. And we benchmarked our method on a variety of hole and electron transfer systems. Let's first look at the hole transfer dataset, the HAB11. And these are organic homodimers, which are fully symmetric. So one can accurately determine the diabatic coupling using high-level electronic structure calculation for the first excitation energy. And our method shows pretty good accuracy for these diabatic couplings in the hole transfer systems. The best performance is achieved with range-separate hybrid functionals, and even when moving to like a pure GGA functionals, the performance is not much worse. While looking at some other available methods, so the fragment orbital DFT method can also give quite accurate couplings, but they are not able to give you variationally optimized diabatic states. And the constrained DFT method is pretty good with range-separated hybrid functionals, but the accuracy somehow degrades significantly when moving to lower tier functionals. And if we use the original MS-DFT scheme to couple the ALMO states, we will get a significant, we will get a consistent overestimation of the coupling. And we also looked at the electron transfer cases. The dataset is called HAB7-, and in general, the trends are very similar to the hole transfer case. And we also tested our method on asymmetric systems, so these two DNA base pairs. We found that our method can give consistent results regardless of the definition of the initial and the final states. And also in general, our method gives the best agreement with reference values. So our method meets all these goals, and we would like to extend this approach to treat photoinduced electron transfer. And this process will involve two different types of diabatic states. One is the locally excited state, which correspond to the electronic excitation localized on the donor species, and also the charge transfer state, which corresponds consequence of the charge separation process. So for the locally excited state, we introduced a method called ALMO-SDF, which combines the variational optimization of ALMOs and the state targeting delta-SDF method for excited states. And for the charge transfer state, if we only focus on the lowest one, then it can be obtained by the ground state unrestricted ALMO calculation, as in the cases of ground state hole and electron transfer. And the coupling between the LE and the CT diabatic states can still be evaluated using the MS-DFT2 scheme. And we tested our method on a couple of systems. And here is a whole transfer in the Indo-Guanine complex. And so here, the hole can be located on either the HOMO or HOMO -1 of the Indo molecule. So these two processes correspond to the ground and excited state hole transfer, respectively. And our method can accurately predict both the diabatic couplings in both of these processes, in both the ground and excited state processes, quite accurately when paired with hybrid functionals, while we found that the original MS-DFT method still overestimates the coupling, especially for the excited state case. And we also tested diabatization based the fragment charge difference diabatization method using TD-DFT states, and it doesn't work very well for this system because TD-DFT states are not of very good qualities for this open shell system. And we also investigate the couplings in the Pentacene dimer, which is a key model system for studies of singlet fission. And the charge separated states, albeit having quite high energies, they are believed to mediate the conversion between the locally excited singlet states and the multi-exotonic states. And here we look at the focus on the coupling between the LE state and the charge separated state. The LE state corresponds to the HOMO-LUMO transition on one of the monomers, and the charge separate state corresponds to moving one electron from the HOMO of one pentacene to the LUMO of another. And we tested the coupling at many different intersystem distances and these monomer rotation angles. And in general, our method, the blue curves, have the best agreement with the previously reported result using the XMC QDPT and the four-fold diabatization method. And yeah, so in summary, I have introduced the development of ALMO-based method to investigate non-covalent interactions and also electron transfer. So the extension of the ALMO-EDA 2 to the solution phase, solvation environment opens the door to the investigation of non-covalent interactions in complex environment, which can be used in many applications, such as like organic reactions. And the development of ALMO and the ALMO-based diabatic scheme we developed offers a way to cheaply compute DFT diabatic states, variationally optimized diabatic states from DFT calculations. And we are currently and accurately calculates the couplings between them. And currently we are using these diabatic states to investigate processes in condensed phase, such as electron transfer reactions. And with that, I would like to thank Professor Martin Hadgod, my PhD advisor, and Professor Tom Markland, my postdoc advisor. And also, I would like to thank all these co-workers who contributed to this work, especially Matthias and Paul for the EDA work, and Andres for the ALMO-based diabatization. And these two developments are supported by two separate NSF grants. And finally, I would like to thank QChem again for giving me this award and the chance to present my research here. And also the method I just presented have been implemented or will be available in QChem soon. So if you are interested, you can check out the most recent versions of QChem. Thank you very much for your attention. Thank you.
Thank you very much. That was a very beautiful talk and lots of new exciting developments and features into QChem that I personally am very, very much looking forward to them. Hello, Yuezhi. Did you consider the solvation entropy and how did you evaluate?
So I think the solvation entropy is currently that is a quite tricky question actually. Yeah, so for the solvent, these implicit solvent models, what we get from the calculation actually it's a solvation free energy, which in principle should include the entropy, so because these solvation models failure to reproduce solvation free energy. Yeah, but I think for currently for the energy decomposition results I show here, they mostly I didn't do like some things like harmonic frequency calculation to calculate the reaction free energy. So these still more like the enthalpy calculation with correction with solvation free energy. So the electronic degree, so the electronic energy is still the is without the entropy correction.
Okay. So there are questions. The solvation interaction is not considered in ALMO-EDA result. If calculation using solvation model is expectable to analyze solvation contribution to int, E and T, I don't know. Please, could you give comments? There is a follow-up question by the same person. Is it possible to assign fragment change and multiplicity for each fragment? Then merge both wave functions to obtain whole transfer also for the ground state and for the excited state. Then compare the energy contributions.
Sorry, so how many questions are here?
The first question is not clear to me. Let's answer the second question. Is it possible to assign fragment, charge, and multiplicity for each fragment?
I think so, yes. Yes, I mean, that's how the ALMO calculation is done, yes.
Okay, and then merge both wave function to obtain whole transfer, also for the ground state and for the excited states. I'm not sure I understand the question.
Think, yeah, that's possible. Yes, I mean, definitely you can, because this for diabatic states, you are supposed to assign like a charge and multiplicity for each of the donor and acceptor species. Yeah.
Another question: have you compared the diabatization results of your formalism ALMO-EDA with constrained DFT on the same system? Can you comment how these two methods compare?
I did. I think so I did that for the ground state hole and electron transfer cases, and so the constrained DFT result I presented here using the default setup in QChem. I'm not sure if the result would change in some other different code, like the implementation of constrained DFT. But here, what we can see is constrained DFT result give quite good couplings when combined with range separate hybrid functionals, but the result is really sensitive to the functional choice. And if you move to even like a global hybrid functional like a B3-lip, you get very large errors. And I think there are for the constrained DFT, there are many different ways to do the partition, and I wonder if the result would change if a slightly different partition method is used. Yeah.
Okay. There is a question. Can this analysis be extended to a strongly correlated systems?
Yeah, that's a very good question. Yeah, so for the ALMO-EDA currently, I think Marlin's group is working on that direction, but I'm probably not so familiar with that. And I think currently what is done is the bonded EDA, which starts from like the high spin, like the high spin fragments, and then it flips the spin in the energy decomposition analysis to create a covalent bond. So this is essentially a EDA of like a cast with a cast-2-2 wave function, and yeah, and I think there are some development on that direction to extend the method to like multiple chemical bonds, but I think that work has not been finished yet. And also, I think there are many different answers for treating like strongly correlated systems, and for example, like a coupled plus valence bond model and the method. And I think, yeah, it will be interesting to further extend the energy decomposition to those cases. Currently, they are not available yet.
Okay, great. Thank you very much from both speakers. Let's virtually join me to thank them. It was a nice session. I enjoyed very much. So I would like to close this session, and thank you very much from everybody to taking the time and being in this session with us.
This concludes our webinar. Thank you for your participation, and see you at the next webinar.